and welcome back. So this is a picture that I was referring to that I think is very complicated to draw all at once, but once you know and remember this stuff, you should be at least be able to draw a rough structure, and I think I'll try and do a summary here to see if I remember it. Okay, so let's start off here. Now, one thing I want to clarify, and I'll have to go back to a few slides. Okay, right, this one, and I just drew this one right now. So you have the inositol ring with all your hydroxyl groups on each of the carbons. If one of those hydroxyl groups gets replaced with a phosphate group, that is referred to as Pi rather than inositol. And this Pi refers to that weird name, phosphatidyl inositol. So one phosphate, and this phosphatidyl is referring to that one phosphate group on number one carbon, basically. And then you start your numbering from there. Okay, so I just wanted to clarify that because it did seem confusing to me when I first looked at this molecule and it said Pi on top of it, and I didn't know why it said that. Oh, anyway, so here's our phosphatidyl inositol molecule with just one phosphate, with just one hydroxyl replaced with a phosphate group. Now I make a kinase catalyze this reaction. So what's kinase? Well, kinases add phosphate groups. So this kinase is going to add a phosphate group on this next position, and this one particularly adds on the fourth position. So now you get 1, 2, 3, 4. So you get phosphate groups on number 1 and number 4 position, and this enzyme is conveniently called Pi4P kinase, and the product is conveniently called Pi4P. So this first P is referring to this first phosphate here, and this 4P is referring to the second phosphate here. So don't think this is just one phosphate group. There's actually two of them in this molecule, right? As compared with the inositol ring. And now we have this Pi4P undergoing another reaction catalyzed by a kinase enzyme and forming Pi4,5P2. So you have three phosphates here, but Pi is, I just want to make that distinction very clear because a lot of people get confused with that. So Pi includes that number one phosphate in itself, so forget about that. Now we're looking at 4,5P2, so 4 and 5, so 4 and 5. So you have your phosphate groups right there. Okay, now Pi4,5P2 is an extremely important molecule, and we'll get to know about that in a second. Let me just erase all of this. Okay. Color red. Okay, so now here's your G protein coupled receptor. When this G protein coupled receptor receives a signal, has a ligand bound to it, this will activate G alpha subunit. Now if you go back to one of those those videos that we did way back, one of the functions of the G alpha subunits was to activate effectors and second messengers and whatnot, and this PIPLC beta is one of the things that it activates. So it was the GQG protein and also the beta gamma subunits that are responsible for activating PLC beta, and we did talk about that in those initial videos, or maybe just a few videos ago. So this activated G protein activates PIPLC beta, and this PIPLC beta, remember what PLC does? PLC breaks the bond between the phosphate group and the glycerol molecule, right? So it divides it into two parts. So you have your glycerol molecule converting into diacylglycerol, okay, and the rest of the inositol, whatever is left, which is the inositol ring, becomes IP3 because it has three phosphates and it has a particular name. It is Pi producing inositol triphosphate. That's what we refer to it because it has three phosphate groups on it. And this is an extremely important molecule because it allows it does something to the calcium ions, which we'll talk about in detail shortly, so we'll leave it for that. So basically it produces this, and then the diacylglycerol. Diacylglycerol is a second messenger, remember, so going back to our previous videos, it will activate protein kinase C, and we haven't talked about protein kinases yet, but we will shortly. Alright, so we'll talk about more about phospholipases in the next video. See you guys there.